There is a metal that the entire nuclear industry threw away for 70 years, treated it like waste, like the leftover ash after you burn the good coal. And for 7 decades, that ash sat in stockpiles, in barrels, in the ground, while the world burned through uranium like it was going out of style. But right now, in a flat stretch of desert, in Wuwei, Gansu Province, China, a reactor is running on that ash. Not uranium, not plutonium, thorium. The element that every nuclear program on Earth looked at in the 1950s, shrugged, and walked past. And this is not a lab demo, this is not a PowerPoint. The Wuwei thorium molten salt reactor went critical in June 2023. It is producing heat right now, today, in 2026. And the plan is not one reactor. The plan is a fleet. If you are new here, hit subscribe. This channel digs into the breakthroughs, the headlines, skip, and the next one drops every week. Hit like if this already sounds like something you want to understand. Let's get into it. Here's the thing about nuclear power that nobody talks about at dinner parties. It is brilliant. And it is also a geographic hostage situation. Uranium-235, that is the isotope that actually fissions in a conventional reactor, and it makes up roughly 0.7% of natural uranium ore, 0.7. The other 99.3% is U-238, which just sits there, mostly inert, taking up space. So you mine a mountain, crush it, dissolve it in acid, spin it through centrifuges at 70,000 revolutions per minute to enrich that 0.7% up to maybe 3 to 5%. And then you build a billion-dollar machine around it. And it works. God, does it work. One uranium fuel pellet the size of your fingertip contains the energy equivalent of about 17,000 cubic feet of natural gas. A single reactor can power a city of 1 million people for 18 months on a fuel load that fits in a swimming pool. The energy density is almost obscene. But here is the hidden cost nobody puts on the brochure. First, geography. About 40% of the world's mineable uranium sits in just 2 countries, Kazakhstan and Canada. Australia has another chunk. You want nuclear power? You need to be friends with those 3, or you need to be them. For a country like China, 1.4 billion people, manufacturing base that eats electricity like candy, that is a strategic leash. A single blockade, a single trade dispute, and your reactors go cold. Second, the waste problem. A conventional uranium reactor produces spent fuel that stays dangerously radioactive for roughly 300,000 years. 300,000. That is not a typo. That is longer than Homo sapiens has existed as a species. And right now, the world's solution for that waste is put it in a pool, then put it in a cask, then put the cask in the ground, and hope the next 10,000 civilizations don't dig it up. Third, water. Conventional reactors need massive cooling. We are talking 30 to 50 million gallons of water per day for a single 1 gigawatt plant. That means rivers, oceans, lakes. It means you cannot build a reactor in a desert. You cannot build one in the interior of a continent where the water table is already stressed. And for China specifically, 60% of its landmass is arid or semi-arid. The coal plants are in the north and west. The population centers are in the east and south. The water is not where the power needs to be. This felt like a problem with no real solution. You either accept the uranium dependency, the 300,000-year waste, the water requirement, or you go back to burning coal and cooking the atmosphere. Until someone went back to the periodic table and picked up the thing everyone else had thrown away. Thorium is not new. It is not some exotic rare earth element that you need a particle accelerator to synthesize. Thorium-232 is about 3 to 4 times more abundant in the Earth's crust than uranium. It is in the sand, it is in the granite countertops in your kitchen, India has 850,000 tons of it. China has an estimated 280,000 tons. The United States literally has stockpiles of the stuff, a byproduct of rare earth mining in Mountain Pass, California, that it has been storing in barrels since the 1960s because it did not know what to do with it. So why did nobody build a thorium reactor 70 years ago? Because in 1954, the United States made a choice. The Navy wanted reactors for submarines. Submarines need compact, high-power density cores. Uranium-235, enriched to weapons-grade or near-weapons-grade levels, gives you that. Thorium does not. Thorium-232 is not fissile on its own. You cannot just put a chunk of thorium in a box and get a chain reaction. You need a driver, a fissile seed, like U-235 or plutonium-239, to kickstart the process. And here's the part that sealed thorium's fate: the Cold War. The military-industrial complex wanted reactors that produce plutonium-239 as a byproduct, because plutonium-239 is what you use to build nuclear weapons. A uranium-plutonium cycle gives you bomb material. A thorium cycle gives you uranium-233, which is technically fissile but is contaminated with U-232, whose decay chain produces gamma radiation so intense it makes weaponization a nightmare. So thorium got a nickname in the nuclear establishment: the proliferation-resistant fuel. Which sounds like a compliment, but in 1955, in the middle of an arms race, it was a death sentence. It meant useless to the military, and the military was writing the checks. Oak Ridge National Laboratory in Tennessee actually built a working molten salt reactor in 1965, the MSRE. It ran for 4 years, it worked, and then Congress defunded it in 1969 because it did not produce plutonium fast enough for the weapons program. The project was shut down, the files were archived. And for 40 years, thorium molten salt reactors became what one nuclear historian called the road not taken and then paved over. India tried. Homi Bhabha laid out a 3-stage thorium program in 1954. But India's nuclear infrastructure was underfunded. Sanctions hit, and the engineering challenges of molten salt chemistry at 700 degrees Celsius were brutal. Corrosion, salt freezing in pipes, tritium management. The problems were real, specific, and unsolved for decades. So thorium sat, the poor man's uranium, the ash, the thing in the barrel that nobody wanted. And then in 2011, the Chinese Academy of Sciences launched the TMSR program Thorium Molten Salt Reactor. Budget, 35 billion yuan over 20 years. Lead institution, the Shanghai Institute of Applied Physics, SINAP. Location for the first prototype, Wuwei, Gansu Province. A flat, dry, waterless stretch of the Gobi margin. They were not trying to build a submarine reactor. They were not trying to make bombs. They were trying to solve the exact 3 problems that made uranium a leash: geography, waste, and water. Here is the reframe. And this is the part that changes everything. The breakthrough is not thorium itself. Thorium is just the fuel. The breakthrough is what you dissolve it in. In a conventional reactor, your fuel is a solid ceramic pellet uranium dioxide sealed inside a zirconium alloy tube. You stack thousands of these tubes into a core, flood the whole thing with pressurized water at 155 atmospheres, and hope the water never stops flowing. If it stops flowing Fukushima, 2011, the pellets overheat, the zirconium reacts with steam, you get hydrogen explosions, and you get a meltdown. The fuel is solid. The coolant is separate, and the system is only as safe as the pump that pushes the coolant. Now, step 1 of the molten salt approach, you take your thorium fluoride THF4 and you dissolve it directly into a molten salt mixture. Specifically, a eutectic blend of lithium fluoride and beryllium fluoride, called FLIBE. You heat that salt to about 650 degrees Celsius. At that temperature, the salt is a liquid. And your fuel is not a pellet in a tube, your fuel is the liquid. The fuel and the coolant are the same substance. Step 2, that liquid fuel salt flows through a graphite moderator core. Inside the graphite, you have your fissile seed, a small amount of uranium, 235, or plutonium, 239, that kicks off the chain reaction. Neutrons hit the U-235, it fissions, releases energy and more neutrons. Some of those neutrons hit thorium, 232 atoms. T232 absorbs a neutron, becomes T233, which beta decays into protactinium, 233, which beta decays again into uranium, 233, and U-233 is fissile. It fissions, it releases more neutrons, and the cycle sustains itself. Step 3, the heat. The fission heats the salt to about 700 degrees Celsius. That hot salt flows out of the core through a heat exchanger, transfers its thermal energy to a secondary loop, and that secondary loop drives a turbine. Standard thermodynamics. The salt then cools back to about 560 degrees and flows back into the core. No pressurized water, no 155 atmospheres. The whole primary loop operates at roughly atmospheric pressure. And here's the brilliant part, the part that makes the old weaknesses disappear. Remember the meltdown problem? In a molten salt reactor, the fuel is already liquid. It is already melted. You cannot melt down something that is already a liquid at operating temperature. And at the bottom of the reactor vessel, there is a freeze plug, a solid chunk of salt kept frozen by an external cooling coil. If power fails, if the pumps stop, if everything goes wrong, the cooling coil loses power, the plug melts by gravity, and the entire fuel salt drains into a passively cooled dump tank below the reactor. No pumps needed. No operator action, no electricity, gravity does it, the reaction stops, the fuel spreads out in the dump tank, geometry kills the chain reaction, and the salt solidifies. Walk away, come back in a week, remember the water problem, the operating temperature is 650 to 700 degrees, you do not need water for cooling, you can use air cooling. You can use a secondary molten salt loop, you can build this reactor in the Gobi Desert, in the Taklamakan, in the middle of nowhere with no river for 1,000 kilometers. That is why Wuwei is in Gansu. That is not an accident. Remember the waste problem? Thorium fission produces far fewer long-lived transuranic elements than uranium. The spent fuel from a thorium cycle is primarily fission products with half-lives in the range of 30 to 300 years. Not 300,000. 300. After about 300 years, the radioactivity drops below the level of the original uranium ore you mined. You can, in principle, store it in a monitored facility for a few centuries rather than a geological tomb for 100 millennia. And the abundance problem? China has 280,000 tons of thorium. At current energy conversion rates, that is enough to power the entire country for over 20,000 years. 20,000. That is not a metaphor, that is just the math. You do not need to import fuel from Kazakhstan. You do not need to enrich anything to weapons grade. You dig it up domestically, dissolve it in salt, and go. The old weaknesses did not get fixed. They disappeared because the substrate changed. Solid fuel became liquid fuel, pressurized water became atmospheric salt, geographic dependency became domestic abundance, 300,000-year waste became 300-year waste. So, is this real? Or is this another, China announces a plan, story that evaporates in 3 years? June 2023? The TMSR LF1, a 2-megawatt thermal pilot reactor, achieved first criticality in Wuwei, Gansu Province. 2 megawatts thermal, small, about the size of a large shipping container. But it is not a simulation, it is not a paper, it is a reactor in the ground with molten salt flowing through it, producing heat. Monitored by SYNAP engineers. By late 2023, the reactor had reached full operating temperature, 650 degrees at the core inlet, 700 at the outlet. The F-Lib salt chemistry held. The graphite moderator performed within predicted parameters. The freeze plug was tested. The passive drain system was validated. Now, 2 megawatts is not going to power a city. It is a proof of concept. But here is what comes next. SYNAP's published roadmap, a 373 megawatt thermal demonstration reactor, roughly 100 megawatts electrical, targeted for the late 2020s. Same site, Wuwei, same team, scaled up salt chemistry, scaled up graphite core, same passive safety architecture, then commercial deployment. The Chinese government's 14th five-year plan for nuclear energy, published in 2022, explicitly names molten salt reactors as a strategic frontier technology. The National Development and Reform Commission allocated funding through the Chinese Academy of Sciences Strategic Priority Research Program, 35 billion yuan total for the TMSR program through 2035. And it is not just SYNAP. In 2023, the China National Nuclear Corporation, CNNC, the state nuclear giant, announced its own molten salt reactor development track, partnering with Tsinghua University's Institute of Nuclear and New Energy Technology, 2 parallel programs, state-backed, funded, timelined. Internationally, the signal is landing. Indonesia signed a Memorandum of Understanding with SYNAP in 2024 to explore thorium molten salt deployment for its outer islands, places where you cannot build a conventional reactor because there is no river. No grid infrastructure, no uranium supply chain. The Philippines has expressed interest. Ghana's Nuclear Regulatory Authority sent a delegation to Wuwei in early 2025, and the patent filings between 2015 and 2025, Chinese institutions filed over 400 patents related to molten salt reactor chemistry, salt purification, graphite moderator design, and freeze plug engineering. The United States filed fewer than 80 in the same period. India filed about 60. The intellectual property gravity has shifted. Right now in 2026, the Wuwei pilot is still running, still producing data, still proving, hour by hour, that the salt does not eat the pipes, that the graphite does not crack, that the tritium stays contained. Every day it runs is a data point that did not exist 5 years ago. And the 373 megawatt demonstration unit, site preparation began in 2025. Concrete is in the ground. The target for first criticality is 2029. This is not a press release, this is a construction site. But here's the honest part of this story. And it matters, because without it, everything I just told you sounds like a brochure. The Wuwei reactor is 2 megawatts thermal. The demonstration unit will be 373 megawatts thermal. A commercial power plant needs to be in the 2,000 to 3,000 megawatt thermal range to be economically competitive with a modern uranium PWR or a gas turbine. That is a tenfold scale up from the demonstration unit, and in nuclear engineering, scale up is not linear. Salt chemistry that behaves in a 2 megawatt loop can behave very differently in a 3,000 megawatt loop. Flow dynamics change, corrosion rates change, graphite irradiation damage accumulates differently when your neutron flux is an order of magnitude higher. The corrosion problem is real. F-Lib salt at 700 degrees is aggressive. It attacks nickel-based alloys. The standard solution is a Hastelloy N variant, a nickel molybdenum chromium alloy that Oak Ridge developed in the 1960s. But Hastelloyen has its own issues. It becomes embrittled under neutron irradiation over time. Synap has developed a modified nickel alloy they call GH3535, and early data from Wuwei is promising, but the long-term irradiation data, 20, 30, 40 years of neutron exposure does not exist yet. Nobody on Earth has run a molten salt reactor at commercial scale for long enough to know what the pipes look like after 3 decades. And the fuel cycle, thorium-232 to uranium-233, is not instantaneous. The protactinium-233 intermediate has a 27-day half-life. That means you need to chemically separate the protactinium from the salt, let it decay in a side loop, and then reintroduce the U-233. This is called online reprocessing, and it is chemically complex. It involves handling highly radioactive fluoride compounds in a continuous flow system. Oak Ridge did it in the 1960s at small scale. Doing it at 3,000 megawatts continuously for 40 years with remote handling robotics in a hot cell, that is an engineering problem that is solved on paper but not yet proven in hardware. None of this erases what the science has already proven. The physics works, the Wuwei reactor's running, but it marks the distance between a 2-megawatt pilot in the Gobi and a 3,000-megawatt commercial plant powering Shenzhen. And that distance is measured in years, in billions of yuan, and in engineering problems that have never been solved at scale by anyone, anywhere. Which brings us back to the bigger picture this whole story has been building toward. For 70 years, the nuclear club was defined by one sentence. You need enriched uranium, you need pressurized water, and you need to be friends with whoever mines the uranium. That sentence drew the map of who got clean baseload power and who got coal. It drew the map of who had energy sovereignty and who had a leash. Thorium molten salt does not just change the fuel, it changes the map. A country with granite in its ground has thorium. A country with a desert has a place to put the reactor. A country with no rivers, no enrichment centrifuges, no uranium import contracts can, in principle, build a reactor that cannot melt down, does not need water, does not produce weapons-grade byproducts, and runs on domestic material for 20,000 years. That is not a technology story, that is a sovereignty story. And it is being written in a flat, dry stretch of Gansu province, in a reactor the size of a shipping container, by a team that picked up the element the rest of the world called ash. The world that ran on uranium did not announce its own ending. It just started losing ground to something simpler, more abundant, and impossible to blockade. So here's the question I will leave you with, and I genuinely want to hear your answer in the comments. If the fuel is in the ground under almost every country on Earth, and the reactor cannot melt down, and the waste is manageable in centuries instead of millennia, what is the actual reason the rest of the world is not building these right now? Is it engineering? Is it politics? Is it that the uranium infrastructure is too big to let go? Or is it something else entirely, something about who benefits from the old map? Drop your answer below. I read every single one. If this made you think, hit like, subscribe, and share it with someone who still thinks nuclear means cooling towers and meltdown nightmares. The next video drops next week, and it is about a material that might make steel obsolete. You do not want to miss it. I will see you there.